As mentioned in the previous video, in this video we will explore the following question. Let V be a vector space over R. Can we characterize all operators on V that has an eigenvalue? From what we saw in the last video, it might be evident that in general this is a difficult question. Therefore, we might look at some alternative questions as well. For instance, we can ask the following question. Can we at least give a sufficient condition? And we will try to answer this question. Now recall that the fundamental theorem of algebra that states that every polynomial has a complex root was crucial in the proof that if V is a vector space over C, then any linear map L from V to V has an eigenvalue. Now, even though we know that in general a polynomial with real coefficients need not have a real root, we know that if the polynomial has odd degree, then it will have a real root. Now there is one nice proof of this using calculus which you might have seen in your course on calculus. If not, we will prove it a little later, but for now let us assume this result. Given this result and what we saw earlier, we might feel that if dimension of V is odd, then any linear operator from V to V will have an eigenvalue. Let us see if we can prove it by following the procedure that we had followed before. So, let V be an n-dimensional vector space over R, let n be odd, and let L from V to V be an operator. Then, as before, we can consider the list of vectors V, L of V, etc. up to L power n of V. As this is a list of n plus 1 vectors on an n-dimensional vector space, they have to be linearly dependent. In other words, there exist real numbers a0, a1, etc. up to an such that a0 v plus a1 L of v plus etc. up to an L power n of v is equal to 0, which we rewrote as a0 into I plus a1 into L plus etc. up to an into L power n acting on the vector v is equal to 0. This reminded us of polynomials, and we could consider the polynomial p of x is equal to a0 plus a1x plus etc. up to an x power n. Now, because n is odd, we know that it has a real root. Say lambda is a real root. Then we know that p of x can be written as x minus lambda into b0 plus b1x plus etc. up to bn minus 1 x power n minus 1. Now, as soon as we have this factorization, we noticed that the linear map a0 I plus etc. up to an L power n is equal to the map L minus lambda I into b0 I plus etc. up to bn minus 1 L power n minus 1. Therefore, if we act V by the first linear map or the second linear map, we will get the same answer. Here notice that when I write multiplication, what I actually mean is composition. Multiplication is just a convenient notation for us. And further notice that this is equal to 0. Therefore, what we see is that the composition of these two linear maps is not injective. Therefore, either this is not injective or this is not injective. If this is not injective, then we see that lambda is an eigenvalue and our proof is complete. However, if this linear map is not injective, then we cannot simplify it any further because this is an even degree polynomial. So notice that in our earlier proof, it was important that we could factorize this polynomial into a product of degree 1 polynomials, which is something we cannot do here. Now we are kind of stuck, and what did we decide we will do in such situations? We decided that we will explore what is the best that we can do. And for that, we will have to understand factorizations of polynomials with real coefficients. Let us take this task next. Let P be a polynomial with real coefficients. If lambda, a real number, is a root of P, then we know that we can write P of x as x minus lambda into some polynomial P1 of x. And we can repeat this process on P1. Therefore, by induction, we can show that if lambda 1, lambda 2, etc. up to lambda m are real roots of P, then P of x is equal to x minus lambda 1 into x minus lambda 2, etc. up to x minus lambda m into q of x. And let us assume that these are the only real roots of P. In other words, let us further assume Q does not have real roots. And let Q of x be a0 plus a1x plus etc. up to ak x power k. By the fundamental theorem of algebra, we know that there exists some lambda in C such that a0 plus a1 lambda plus etc. up to ak lambda power k is equal to 0. But notice, as the conjugate of 0 is itself, we know that the conjugate of a0 plus a1 lambda plus etc. up to ak lambda power k is also equal to 0. If you are not familiar with the word conjugate, conjugate is a very simple operation. Given a complex number a plus ib, its conjugate is defined as a minus ib. But the conjugate of sum of numbers is equal to sum of their conjugates. In other words, this is equal to a0 conjugate plus a1 lambda conjugate plus etc. up to ak lambda power k conjugate. Similarly, the conjugate of a product of two numbers is equal to product of their conjugates. Therefore, this is equal to a0 conjugate plus a1 conjugate into lambda conjugate plus etc. up to ak conjugate into lambda conjugate whole power k. And further notice that as a0, a1, a2, etc. up to ak are real numbers, their conjugate is same as itself. Thus, this is equal to a0 plus a1 lambda conjugate plus etc. up to ak lambda conjugate whole power k. Thus, it is evident that lambda conjugate is also a root of Q. Thus, we can write q of x as x minus lambda into x minus lambda bar into q1 of x, where q1 of x is some polynomial. But x minus lambda into x minus lambda bar is equal to x square minus lambda plus lambda bar into x plus lambda into lambda bar. And further notice that both lambda plus lambda bar and lambda into lambda bar are real numbers. In fact, lambda plus lambda bar is the real part of lambda, and lambda into lambda bar is the modulus of lambda square. Therefore, we see that this is a polynomial with real coefficients. Therefore, if we prove that q1 has real coefficients, then we would have factorized q into product of two polynomials with real coefficients. So we will next prove that q1 indeed has real coefficients. Notice that for every real number x, q of x is also a real number. Similarly, x square minus real part of lambda into x plus modulus of lambda square is also a real number. Thus, the quotient of these two numbers will also be real. Thus, q1 of x is real for every real number x. In other words, for every x in R, the imaginary part of q1 of x is equal to 0. Thus, if q1 of x is equal to b0 plus b1x plus etc. up to bk minus 2 x power k minus 2, then we know that the imaginary part of q1 of x is equal to the imaginary part of b0 plus etc. up to the imaginary part of bk minus 2 into x power k minus 2. And we know this is equal to 0. Thus, we see that this polynomial is identically equal to 0, which implies that all its coefficients are equal to 0. In other words, imaginary part of b0 is equal to 0 and so on up to imaginary part of bk minus 2 is equal to 0. It's a good idea to ponder why this implication is true. It once again follows from the fundamental theorem of algebra, or the fact that we can write any such polynomial as a product of degree 1 polynomials. This would imply that any such polynomial can have at max k minus 2 roots. But on the other hand, every real number is a root for this polynomial. So all the coefficients have to be equal to 0. And if the imaginary part of b0 is equal to 0 and so on up to imaginary part of bk minus 2 is equal to 0, that would imply that b0, b1, etc. up to bk minus 2 belongs to R. In other words, q1 is a polynomial with real coefficients. As q1 of x is also a polynomial with real coefficients, we can repeat this procedure. And thus, by induction, we will be able to write q of x as a product of quadratic polynomials. More precisely, I will be able to write q of x as c times x square plus alpha 1 x plus beta 1 into so on up to x square plus alpha lx plus beta l. Combining with the fact that p of x is equal to x minus lambda 1 into etc. up to x minus lambda m into q of x, we can write p of x as c times x minus lambda 1 into etc. up to x minus lambda m into x square plus alpha 1 x plus beta 1 into so on up to x square plus alpha lx plus beta l. This means we can also factorize the linear map a naught I plus etc. up to a n l power n as c times l minus lambda 1 I into so on up to l minus lambda mi into l square plus alpha 1 l plus beta 1 I into etc. up to l square plus alpha ll plus beta li. Thus, if we act either of the linear maps on V, we will get the same result. But we know that this is equal to 0. Therefore, the composition of these functions is not injective. So at least one of these functions has to be non-injective. Notice that L minus lambda I is not injective implies that lambda I is an eigenvalue. And we will be done if we can prove this. But we won't be able to always conclude this. It is also possible that these are all injective, but one of these are not injective. Let us see what we can say in that case. We know a linear map is not injective if and only if its null space is not equal to the singleton set 0. Therefore, if L square plus alpha jl plus beta ji is not injective, then we can say that there exists some vector v in the vector space V such that L square plus alpha jl plus beta ji acting on the vector V is equal to 0. In other words, we know that L square acting on V plus alpha j into L acting on V plus beta j into V is equal to 0. In other words, L of V is equal to minus alpha j times L of V plus minus beta j times V, which implies that L of V belongs to the span of V and L of V. And this implies that L of span of V and L of V is a subset of span of V and L of V. Now notice that V is an eigenvector if and only if L of span of V is a subset of span of V. Now, doesn't this look very similar to this? Therefore, this property can be thought of something analogous to the property of being an eigenvector. And thus, we will give a special name to subspaces that has this property. More precisely, we say a subspace U of a vector space V is invariant under an operator L if L of U is contained inside U. And the discussion we have had so far can be summarized as follows. If V is a non-zero vector space over R, then every operator on V has an invariant subspace of dimension 1 or 2. Let us quickly recall why this was the case. We first obtained an equation 0 is equal to a naught I plus etc. up to a n L power n acting on the vector V. Then we factorized the polynomial as c times L minus lambda 1 I into etc. up to L minus lambda mi into L square plus alpha 1 L plus beta 1 I into etc. up to L square plus alpha LL plus beta Li acting on the vector V. And from this equation, we concluded that the composition of these linear maps is not injective. Therefore, at least one of these linear maps has to be non-injective. If it is one of these maps that are not injective, then we get an invariant subspace of dimension 1. On the other hand, if it is one of these maps that is non-injective, then we get an invariant subspace of dimension 2. And that is the idea of the proof. Before we end this video, let us look at some examples of invariant subspaces. Throughout this discussion, let L from V to V be an operator. Then the null space of L is an invariant subspace. Why is this the case? This is because if V belong to null space of L, then L of V is equal to 0 and 0 belong to null of L. Similarly, notice that range of L is also an invariant subspace. This is actually even more trivial. Why? Because irrespective of whether V belongs to range of L or not, T of V will always belong to the range of L actually. So in particular, if V belongs to range of L, T of V will belong to range of L. So range of L is also an invariant subspace. Let us look at one more example. Given an eigenvalue, its eigenspace is also an invariant subspace. More precisely, the set of all vectors V in V such that L of V is equal to lambda times V is an invariant subspace. Why is this the case? Notice that L of U is equal to lambda times U implies that L of U is equal to L of lambda times U, which is equal to lambda times L of U, which implies that L of U belongs to the set of all V belongs to V such that L of V is equal to lambda times V. I hope that with these examples you have a better understanding of the concept of invariant subspaces.